What is up, everybody? Welcome to chapter 4 of chemistry. This chapter we were talking about electrons. I think I haven't recorded for such a long time. I might forget something, but this chapter we're going to be talking about electrons and like the ways to write orbitals, right? So there are two. Before we generate electrons, before we observe electrons, we have to find out where they came from first. So there are two ways of generating the visible light. You could either heat the object super hot or pass an electric current through a sample of matter, right? So the hotter the object gets, the higher the light goes. If you microwave fire, you get plasma in the microwave, which is definitely not safe. Do not try it at home. But that the temperature of that is around 10,000 degrees, 10,000 degrees Celsius, which is really, really hot. It's hot enough to rip electrons, right? Microwave a fire, and you'll get plasma. And that's an example of UV light, right? Ultraviolet radiation, which you shouldn't even come close to. You have a high chance of skin cancer, right? Anyways, so there are two ways of generating visible light, right? And the other way is passing electric current through a sample matter. That's where we get the electrons from. See, when light passes through a prism, which is kind of like a mirror, right, which kind of just resembles the electrons, right? But this is actually a prism, it's not a mirror. There's a continuous spectrum of light. However, when electricity is passed through, only certain light frequencies are emitted. Now, the certain light frequencies, the light represents the energy of the electron. The light represents the energy of the light, or the energy of the photon. That's what it's called, right? Light is photon. So, why is there that certain light frequencies are emitted whenever electrons are passed through a gas? Why are only certain light frequencies emitted? So there's a guy called Niels Bohr, and he proposed that atoms don't have random energy. They come in discrete packs of energy, called n, right? Um, or represented by the number n, right? And he suggested that the amount of energy emitted in electrified hydrogen was equal to the difference in energy of the electron's energy states. That seems really confusing, right? It probably is. But basically, it's if you have an electron and you have two energy states that it could two energy each electron has two energy states that it could be in, and if you subtract the highest to the if you send an electronic signal into it, it moves from it moves from a high energy state to a low energy state, or the other way around, I'm not sure, but that emits electricity, right? No, it probably moves from a higher energy state to a lower energy state, and it emits a little bit of light um, from that energy state movement, right? So, for example, hydrogen, right here, right? The lower the wavelength, the higher its energy state. So these light spectrums of hydrogen is equivalent to how whenever um, the light that it shows is equivalent to how much energy it's emitting, right? And you can't really calculate it right now. There might be a way you might see in your physics class how to calculate how much energy an electron gives off whenever it shines a certain amount of light. I'm not going to try to do that right now. It's called quantized energy because the amount of energy is constant, right? There's discrete packs of energy, and it's not random energy, neither is it fluctuating energy, right? So the Bohr's model of the atom is we've already kind of discovered it. We've already kind of generalized it as just like a bunch of rings around um, an orbital, or a bunch of rings around a nucleus, a bunch of orbitals, right? Which actually does appear in the real, what we think is real quantum model of the atom right now. But it's just not true that orbitals appear in rings, two-dimensional rings especially, right? Even three-dimensional rings. It's just not true, right? The electrons are regarded as both waves and particles, so they are not restricted in certain orbits, and you can never ever find both the momentum and the position of an electron at the same time, because momentum is basically how much it's going multiplied by its weight, and the position is where it is at. So you can't find where an electron is going and where it's at the same time, which is which is the bare blocks of quantum mechanics. And if you guys like quantum mechanics and just don't like taking chemistry, then just go do quantum mechanics. I don't know why you're still here, but this is like an introduction to quantum mechanics. If you find it cool, put it in the comments. Maybe I'll do another course, one course in quantum mechanics. It'll be undergraduate college level, which will involve a lot of math and differential equations. So it won't be easy. But if you want quantum mechanics on this channel, subscribe to the channel and leave a comment saying that I should do quantum mechanics. So, scientists actually discovered that there were four quantum numbers, or four things that govern the quantum, the position and momentum of the electrons, not just one, right? So the first quantum number is called the principal quantum number. It's called n, and n can be any natural number, and n basically just signifies it it just sets the ground for what other quantum numbers there can be, right? So it's kind of like a limiting factor, right? And the second quantum number is called the angular momentum quantum number, or which is L, right? And L contains a little bit of the energy. N contains most of the energy in the electron, but L contains only a little bit of the energy. But it basically also dictates how the electron is going to move in three-dimensional space. So L can be any number from 0 to n minus 1. So for example, in the n, in the n equals 1 case, L is equal to 0. No excuses, no shortcuts, right? N equals 2, L is equal to 0, 1. N equals 3, 0, 1, 2, 0, 1, 2, 3, 0, 1, 2, 3, 4. And we assign names to subshells, and the subshell is basically just a shell in which the electrons move in, orbit in, and of high probability. It's a shell of high probability that the electrons orbit in, because the electrons don't actually have to be close to the atom in order for the atom to work, right? And the electrons don't have to orbit in certain positions, and the atom can still work with the electrons even if it's really far away. So you could technically have an atom on one side of the universe and its electron on the other side, and it would still work. And that's how crazy quantum mechanics is. But we're gonna get back, and we have our subshells. We have S, P, D, V, F. You'll know what those are later. Actually, you'll know what those are later today. S is correspond to L equals 0. P is correspond to L equals 1. D corresponds to L equals 2, and F L equals 3. Right? The third quantum number is called ML, which is magnetic quantum number. It's a magnetic quantum number, and it depends on L, right? So if L equals 0, ML can be 0. If L equals 1, ML can be -1, 0, or 1. If L equals 2, -2, -1, 0, 1, 2. So it's basically ML, or ML, the absolute value of ML. Oh my god, I suck at freaking writing. Okay. The absolute value of ML has to be lower than or equal to L. And that is, that's the formula. right? You could learn that formula. You could use that formula quite easily, right? So 2 can be -2, -1, 0, 1, or 2. And the ML, the quantum number, is just signifies what orbits they're in, or how many orbits there are, right? So for example, ML L of 0 has only one orbit because it has only 0, right? So it's like that. And then this has 3 orbits. The 3 orbits look like that. One is kind of x phase, one is y phase, one is z phase. And then this one, one is x phase, one is x squared minus y squared phase, which is circular. One is x phase, y phase, z phase, and one is I don't even know what that is. Z squared. I don't know what that is. But yeah, these look quite weird. They look quite weird. They look quite amusing. And if you have combinations of them, they would. It's just absolutely crazy. Orbitals, right? So the last quantum number is the spin quantum number, n sub s, and it decides the spin of the electron. So it can go up or it can go down. If it goes down, it's the value is -1/2, and if it goes up, the value is +1/2, right? So just by these, we can kind of just determine how many electrons are possible in each L level. For example, L equals 0, we have only one ML value, and each ML value can only have two MS values, two spin number values. So that's 2, right? And L equals 1, ML equals 3. So possible electron configurations for L equals 1 is 6. Possible configuration for L equals 2 is 10, 14, 18, 22, and keeps going, right? But I don't think no scientist has discovered any farther than the F orbital yet. At least that's one I think. There might be more orbitals that we just haven't discovered yet, and they look pretty cool, right? Just the S, P, D, and F ones look really cool, and I'll show you the F ones later. Maybe, probably not though. But they look really cool, right? So let's answer some questions. What are the possible values of L when n is equal to 5? So when n is equal to 5, L has to be 1 less, all the way from 0 to 1 less than n. So it's 1, 0, 1, 2, 3, and 4. And we could calculate the number of possible electrons, which is pretty ridiculous. N is equal to 1, L can only be 0. When ML is equal to 3, no, when L is equal to 3, oh god, I really hate writing these L's. I want to write regular L's, but if I write regular L's, it'll look like I. L is equal to 3, ML can be -3, 2, -1, 0, 1, 2, or 3. And when L is equal to 6, ML can be equal to -6, -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, and 6. Yeah. 13. Describe the shape of an s orbital. Let's go back. We're gonna go back. The s orbital looks like a sphere, right? This is the s orbital right here. This is an s orbital, right? S. And then next to p, and then next to p. But this is an s orbital. It looks like a sphere. So, sphere. Describe the shape of a p orbital. It looks like 2 lungs or 2 blood cells, right? 2 blood cells. Or 2 lungs. Or 2 hands when you put them next to each other, right? It basically just looks like, I'm just going to use technical terms, 2 ellipses next to each other. Yeah, I'm just going to write next. Which of these set of quantum numbers not allowed? And if it's not, explain why. So n equals 4. N equals 4, right? This is the first one. So n is equal to 4. Then L can be equal to 0, 1, 2, 3, and 4. So it's equal to 1. L is equal to 1. So that's allowed, right? So then ML can only be -1, 0, or 1. And it's -1, 0, 1, but there's -2 in here, so this is not allowed. Not allowed. Next, 5, 2, -1, and -1/2. So we have n is equal to 5, so L can be equal to 0, 1, 2, 3. Actually, I forgot. It's -1, so this isn't 4. I'm sorry. It's gonna be 0, 1, 2, 3, or 4, and then it is 2, so that's allowed. And so ML can be -2, -1, 0, 1, or 2, and it is -1. And each ML can have 2, and as long as it's 1/2 or -1/2, it's allowed. So this is allowed, right? Boom, done. That's gonna be it for today's episode. If you liked it, press the like button. I'm gonna be recording 4.2 literally like right after this. And I hope you have a good day. Bye.